Hey everybody, in this video we are going to talk about another way we can calculate delta H. But first we have to learn about bond enthalpy. Bond enthalpy is the amount of energy it takes to break a mole of a bond in the gas phase, and this part is very important. Since they involve breaking bonds, which takes energy just as breaking a candy bar might take energy, then bond enthalpies will always be positive, so the process is always endothermic. As an example, let's take a look at this CH bond in the gas phase. The 1 mole of CH bonds will be broken down into a mole of C and a mole of H. And the change in enthalpy associated with this reaction will be the delta H, or the bond enthalpy for the carbon-hydrogen single bond. And it turns out, according to the table, the bond enthalpy for the CH bond is going to be 413 kilojoules per mole of CH bonds. And this reaction shows this since this is 1 mole of CH bonds per 1 mole of CH. And you could think of it this way: 1 molecule of CH has 1 CH single bond, so a mole of CH will have a mole of CH bonds. Now let's take a look at something more complicated, something like methane Ch4. Now 1 molecule of CH4 has 4 CH bonds, so a mole of CH4 would have 4 moles of CH bonds, and when you break this apart you get 1 mole of C and 4 moles of H, and note that they're all in the gaseous phase. So the delta H of this reaction would be equal to 4 times the delta H for breaking the CH bond, and the reason for this is because instead of breaking just 1 mole of CH bonds, which is the delta H for the CH bond, you're instead breaking 4 times as many CH bonds. So the enthalpy of the reaction will be 4 times that of the bond enthalpy, which describes just 1 mole of bond broken. And since there are 4 moles of bonds broken, then it's going to be 4 times the bond enthalpy for the CH single bond. And note that this is based on intuition and not Hess's law. If it was Hess's law, then we would have a 4 here, but of course we don't, and that's why this is based on the number of bonds you break rather than something like Hess's law where you look at the coefficients. So now let's get into a related topic that has to do with bonds. So typically, the stronger the bond, the higher the bond enthalpy. This makes sense because it takes more energy to break bonds that are stronger. So there are 2 main things that determine bond strength. The first thing is the number of sigma and pi bonds. Note that a single bond is weaker than a double bond, which is weaker than a triple bond. And this is because the more bonds there are, the more connections there are between the 2 atoms via shared electron pairs, which add reinforcement to the overall bonding between the 2 atoms. So if you remember, a single bond just has 1 sigma bond, a double bond has a sigma and a pi, and a triple bond has a sigma and 2 pi. And notice that this has the most amount of bonds, quote unquote, and thus it will generally be the strongest bond. Now the second thing that determines bond strength is the length of the bond. Now this is because the closer the nuclei are, the stronger the electron-proton attractions are between the atoms, and this strengthens the bond between them. And this is all because of Coulomb's law, which states that the closer 2 things of opposite charges get, the stronger the attraction between them. And from this we can conclude that stronger bonds are typically shorter, while weaker bonds are typically longer. So let's compare two bonds. The first bond is a single bond between two carbons, and the second bond is a double bond between two carbons. Now this one is going to be stronger because it has a sigma and a pi bond, while this one only has a sigma bond. So that's reflected in the delta H of the bond enthalpies, and this is because this bond enthalpy is higher than this bond enthalpy, which tells us that this bond is harder to break and requires more energy to break the bond. Now, let's compare the bond lengths. So the double bond is going to be shorter than the single bond, and this is because stronger bonds correlate to shorter bond lengths. And since this has a higher bond enthalpy, aka it's a stronger bond, then this will have a shorter bond length. Now let's compare CH and the CC single bonds. Which one would be stronger? Well, I think that this one would be stronger because the C and the H are located more closely to each other than the C and the C. So let me label the atoms. There you go. And notice how the bond length is longer here than for here. And because of that, this one has stronger electron-proton attractions, which strengthens the bond. And that's why the delta H here is greater than over here. And that's why, since this one is a stronger bond, the bond length is going to be shorter than the bond length for carbon-carbon, as illustrated in these two pictures. So when you draw atoms or ions, you could just draw huge spheres for simplicity, and yeah, I mean, those are their electron clouds, so it is a good representation of them. So you might be wondering, why do we care about bond enthalpy? Well, it lets us predict the approximate delta H of a few reactions. So the first thing we are going to consider is going to be the reaction between H2 and F2 to make 2HF. Notice that you have to balance all your reactions. So balance, and this applies to almost everything. Just balance if you can. I mean, just do it. So balance, balance, balance. And before we begin, note that bond enthalpies should be used for a reaction where all the components are gases. Since all these are gases, we are good. Now, the first step to doing problems like this is drawing. So we gotta draw out each of these chemicals, and they all are quite easy to draw, and I drew them for you. So now let's count the number of bonds. So in one molecule of H2 gas, there's one HH single bond. So in 1 mole of H2 gas, there's 1 mole of HH single bonds. So 1 mole of HH single bonds. Over here we have 1 FF single bond, so 1 mole of FF single bonds. And over here we have not 1 mole of HF single bonds, we actually have 2 moles of HF single bonds, since there are 2 moles of hydrogen fluoride. And note that I called it hydrogen fluoride and not hydrofluoric acid, since it's in the gas form. Now, let's go on to the next step. So, over here, things are going to get a little bit creative. On the left-hand reactant side, we are going to imagine that we are going to break all the bonds, and the values for the enthalpies for these processes will be positive, since breaking bonds takes energy, and you have to find the total change in enthalpy considering the coefficients. Now, I'll show you how this works, but before I do that, I want to talk about the products. So, on the product side, imagine that after breaking all the bonds here, you are reforming them or creating them over here, and creating bonds will not take energy. Instead, it will release energy, and therefore the bond enthalpies should be negated to create the desired, process that the product side is describing. So on the product side, we are creating bonds, so it's the opposite of breaking bonds, which is what bond enthalpy is describing. So over here, bond enthalpy, which is it's describing the breaking of bonds. Now, what if we wanted to form the bonds, which is what's happening on this side? Then we would flip the reaction and have two atoms combine to form a bond. Notice how when you flip a reaction, the delta H is negated, so therefore we have to use the negative version of the bond enthalpies on the product side. So now that we know this, let's actually look at how this is exactly done. So over here, I have the bond enthalpies for each bond, and they're all in kilojoules per mole. And in order to do the math or the overall change in enthalpy for the system, we have to consider the amount of energy it took to break these bonds and the amount of energy that we got back from creating these bonds. So we broke 1 mole of HH and 1 mole of FF. So 1 mole of HH is shown over there. 1 mole of FF is shown over here. And notice how we're multiplying by 1 mole. And on the product side, we are producing 2 moles of HF. So we are creating 2 moles of HF bonds as shown here. So if we create bonds, remember we have to negate it since it releases energy. So this will be in the negative form. And each mole of HF releases 567 kilojoules. So we have 2 moles of HF, so we multiply 2 moles times that. And adding these two processes up, we get that the change in enthalpy for this reaction is 24 kilojoules. And the official answer would be 24 kilojoules per mole of reaction, because 24 kilojoules is describing the change in energy for this process specifically for this reaction. So you have to write per mole of reaction to specify, 24 kilojoules is referring to that reaction. So now let's read this little note that I wrote. The idea of breaking and reforming bonds and adding up the change in enthalpy for those two processes works because no matter how we get from reactants to products, whether we break and reform bonds or whatever we do, the delta H of the reaction will always be the same since enthalpy is a state function and the difference of enthalpy between the products and reactants will remain constant. So this is a similar explanation to Hess's law, which was basically when we had 2 or more chemicals to start off with, and it didn't matter what path we took because in the end, the products would be the same and the change in enthalpy, no matter what paths you took, those paths would add up to the change in enthalpy for the net reaction. So same thing going on over here, but just a little bit different. So now that we're done with this problem, let's actually do one more question. So this question is going to be a little bit tricky, I admit, but we can do this because we can overcome any challenge, right? So this reaction is the reaction we want to find the delta H for. And notice that there are liquids in this reaction, and bond enthalpies only work when the chemicals are gases. So are we done for? Well, not exactly. We still have some hope. So how about this? Let's start off by writing this reaction as if they were all gases in order for us to use bond enthalpies. So we draw out the Lewis structures, not that bad, and then we count the number of moles of bonds. So on the left-hand side, we have 2 OH single bonds and 1 OO single bond. And since there are 2 moles of hydrogen peroxide, then we double it. So in the end, we have 2 times 2, which is 4 moles of OH single bonds, and 2 times 1, which is 2 moles of OO double bonds. Now on the right-hand side, we have 2 moles of OH single bonds in water, but we have 2 waters, so we double that. So 2 times 2 is 4 moles of OH single bonds, and we have 1 mole of OO double bonds. So now that we have these values, and we also have this neat table to guide us through this challenge, we can now find the overall enthalpy of the reaction in terms of gases. So on the left-hand side, we are breaking the bond, so they will all be positive values. So 4 times the bond enthalpy for 1 mole of OH single bonds, plus 2 times the bond enthalpy for the OO single bond, plus 4, because there are 4 moles of OH bonds on the right side, times not positive 463 kilojoules per mole, but negative 463 kilojoules per mole, since we are creating bonds on this side, so we have to negate all the bond enthalpies on the product side. So instead of being positive, we will use a negative. So 4 times negative 463 plus 1 times the bond enthalpy for OO double bonds, but we have to negate it since we are on the product side, so it's a negative number. And doing this neat math, we get that the change in enthalpy for this reaction is negative 203 kilojoules per mole of reaction. Remember, we got to add this at the end. But wait, we're not done, because remember, the reaction was in terms of liquids and not all gases. So we have to find a way to use Hess's law to convert these gases into liquids, and the delta H, of course, will change because of that. So our very first reaction will be the reaction we just wrote out. The 2H2O2 becomes 2H2O plus O2, and we calculated the delta H for that. And what I will do to change the H2O2 gas into H2O2 liquid is use the delta H of vaporization and the corresponding reaction. So the delta H of vaporization is the conversion between a liquid and a gas. So I Googled it and I found the delta H of vaporization for this reaction in kilojoules per mole, because we want to keep the kilojoules consistent. And notice that we want to cancel out the 2H2O2 gas up here and change that into 2H2O2 liquid as in the original reaction. So what we can do is double everything, times 2, and the delta H of vaporization is times 2. So the delta H of this reaction, which is labeled as reaction number 2, will be 97.0 kilojoules per mole. Now reaction 3 is converting this gas into a liquid, because in the original reaction that we wanted the delta H of, the H2O was a liquid. So we have to find a way to convert the gas to a liquid. Well, we could start off with the delta H of vaporization for water, which is 40.65 kilojoules per mole, and it describes H2O liquid becoming H2O gas. So how do we make it so that the H2O gas on the right-hand side is canceled out? Well, we could flip and multiply by 2. And by doing that, the H2O gas has a coefficient of 2 and is on the left-hand side to cancel out with the right-hand side, which is over here. And the delta H will be negated and multiplied by 2. So 81.30 kilojoules per mole is the new delta H of this reaction. So reaction 1, 2, and 3. On the next slide, I simply rewrote them. And now, let's just use Hess's law. So Hess's law will hopefully work out. And if it doesn't, we will try again. But I think it will work out since I did this already. So, looking at this, we notice that the 2 H2O gases will cancel out. We notice that, what else cancels out? Oh, these two cancel out. And we're left with 2 H2O2 liquid becomes 2 H2O liquid plus O2 gas. And notice that by doing Hess's law, by adding up all these delta H's, we get that the delta H of the reaction is negative 187 kilojoules per mole of reaction. Never forget the mole of reaction, since delta H is founded upon that. And in the last video, where we used the heats of formation, we calculated that the delta H of this reaction was negative 196.0 kilojoules per mole of reaction, and that was at the standard state. So, if you notice, all 3 of these delta H's were not in the same conditions, And this is because this reaction happens at the boiling point or the vaporization point of hydrogen peroxide, and this happens at the vaporization point of water, and they're at different temperatures. So notice how I broke a little rule, and in the last video I said that you can't add up delta H's that are at different conditions, but this time I did, because honestly I had no choice, and I don't know how to calculate the delta H's for these reactions at the same conditions. I can only do them for different conditions based on the data I was given. So I kind of gave myself some room for error, but that's fine because in the end, the two delta H's were pretty close to each other, and this goes to show that bond enthalpies are an excellent way to calculate the delta H of reactions since both of them give around the same result. So that's all for this video. Have a nice day.